All right, so this will be the last section for Unit 5, Unit 5.6. This will be special segments in triangles, okay? So we're going to talk about some different lines that we see that occur in triangles, and they have different properties for each one of them, and some of them we'll see have other unique features about them. So let's get straight into it with the very first one. So we're going to first talk about an altitude in a triangle. So let's look. Okay, so as you can see on these notes, there is a lot of information in here. Okay, so there's going to be a few key points that I really want you to key in on. But starting out, so an altitude is going to be a segment from a vertex that is perpendicular to the opposite side or to the line containing that side. So what that means, an altitude is always going to start at one of the vertices. It's always going to start at one of the points. And it's going to be a line that drops down from the vertex and is perpendicular with the opposite side of the triangle. Okay, so that's the main key features. It starts from a vertex, it drops down, and it is perpendicular, which means it creates right angles. Okay, so in a triangle, I can draw all three of my altitudes, like in this one right here, and the point where they all intersect at. So for example, in this triangle, that point there, this is known as the orthocenter. Okay. And one key feature here is that the altitudes, whenever they intersect, they can intersect inside, on, or outside of the triangle. So in this one, it's a special circumstance where they intersect inside the triangle. But depending on how the triangle is shaped, depending on how long some of the sides are, they may all intersect right on top of one of the sides, maybe like right here, or they could even intersect all like outside of the triangle. Okay, so let's look down here. So another key fact right here. So we see right here, so my triangle here is right here. For this example, this is what my triangle looks like. But as you can see, my altitude is actually right here. This is my altitude for this vertex. So in some triangles, the altitude may actually get drawn outside of the triangle. So if we look at this point, there is no way that I could draw a line opposite to this side. So there's no way I could draw a line from this vertex to this side and it be perpendicular. But the good thing about altitudes is that you can extend the side. So that's what they did here. They extended this bottom side with this dashed line right here. And so then I was able to draw my altitude and create that right angle. So your altitudes are always going to start from a vertex, and they're always going to drop down and be perpendicular with the other side, or with the opposite side. And sometimes you may have to extend that side so that you can draw it. Okay, so let's look at an example. Okay, so in this example, we're told that segment HA is an altitude of triangle HJK. We need to find x, the measure of angle HAJ, and the length of segment JK. So if we look, HA is an altitude, so HA is this line right here. That's my HA. And I'm told that this is an altitude. So an altitude is always going to start from a vertex, so it's starting at point H, and it is going to drop down and be opposite with the other side. And it's going to be opposite with it in such a way that it is perpendicular. So HA is perpendicular with this side of the triangle, JK, which means it creates right angles. All right, so how does that help me? Well, I need to solve for x. So I've got an x here and an x here, and then I've also got an x here. So I don't really know anything about this side of the triangle, which is what x plus 8 and x minus 9 are representing. But what I do know is I know something about this angle right here. So this 3x plus 3 degrees angle is one of the right angles that's created from my altitude. So I can set 3x plus 3 equal to 90. So once I do that, subtract my 3, I'll get 3x is 87, and then divide by 3, and I'll get x is equal to 29. So now I want to figure out what is the measure of angle HAJ. Well, the measure of angle HAJ is that same angle I just worked with, 3x plus 3. So even if I hadn't already solved for x, I also know that HAJ is one of my angles that was created by my altitude intersecting with this side of the triangle, meaning it was a 90-degree angle. So measure of angle HAJ is just 90 degrees because altitudes are creating right angles, and that angle is one that was created. Last up, I want to figure out what is the length of segment JK. So it won't always be like this way in most problems, but in this specific problem, the x that we solved for here will also work for these two segments. So keep in mind, the segment JK is this whole thing. Okay, x plus 8, that represents JA, and x minus 9 represents AK. Now, we don't necessarily know if JA and AK are equal to each other. Kind of looks like it if we eyeball it, but we can't be for certain on that. But one thing we do know is that because of segment addition postulate, JA plus AK equals JK. So JK is going to be equal to x plus 8 plus x minus 9, just taking these two and adding them together. Now I'm going to plug in 29 for x, so I get 29 plus 8 plus 29 minus 9, and that's going to wind up being 57. So JK has a length of 57. All right, so the next segment that we'll talk about is an angle bisector in a triangle. So an angle bisector, that is something that we've seen a decent bit. We saw it back in Unit 1, and we've seen it a little bit since. So an angle bisector, it basically does exactly what it says it will do. Okay, it bisects an angle. Okay, and keep in mind, bisect just means cut in half. Okay, so for this example right here, this segment is an angle bisector. So with the angle bisector, it's always going to touch one of my vertices. Okay, and it's always going to do that because it has to cut the angle created from the two sides of me to that vertex. So an angle bisector will always start at one of my vertices, and it will always cut the angle in half. So in this triangle right here, they drew all of my angle bisectors, okay? So you notice that every single one of these, they're always going to intersect inside the triangle, okay? And so the point that each of these intersect at, that's going to be known as the incenter, okay? And then one little cool fact right here is that the incenter, so this point, is equidistant from the three sides of the triangle. Okay, so what that basically means is that if you look from this point to each of the sides of the triangle, there's a little short length, and that length is all going to be equal to each other. So that's what the incenter. Okay, so with angle bisectors, we've also got two little theorems that we're going to be looking at. Okay, so first up, the angle bisector theorem, which states that if a point is on the bisector, no, it's a little bit covered up, but if a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. And then the converse of that, we talked about what a converse was back in Unit 3. The converse of that is if a point is in the interior of an angle and it's equidistant from the sides of the angle, then it lies on the bisector of the angle. So if we look right here, find the value of x in this example. So we have down here that this angle has been bisected. It's been cut in two. We know that because they put one curve on each of those little half angles, so we can assume that those are going to be equal. So my angle bisector theorem tells me if a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. Okay, so we look, my angle bisector is this line right here. That's my angle bisector. Okay, so what this theorem is telling me is that if I just choose any random point that is somewhere on this line, then it is the same distance from both sides of the triangle. So basically, if I was to pick maybe this point right here, and then if I was to draw the distance from the two sides of the triangle, or the two sides of the angle, because the angle is made by this side and by this side, this point will be the same distance from both sides of the angle. That's what my angle bisector theorem is telling me. Well, if I look at my problem, if we pick another point, let's pick this point up here. So this point up here, again, is going to be the distance from this point to this side of the angle, and this distance, or in this point from this side of the angle, those are going to be two equal distances. That's according to my angle bisector theorem. So if these two lengths are the same, I can set their measurements equal. 10x minus 10 is equal to 8x. Subtract 8x and add 10, so 2x will equal 10. And then lastly, divide by 2, so x will equal 5. So that's just using our angle bisector theorem. Okay, now let's look at this second example. Point G is the incenter of triangle ABC. So this is point G right here. And then we're told if GC has a length of 25 and EG has a length of 7, what is the length of DG? Okay? So with this one, they actually give us some information that we don't necessarily need. So look back up here. We talked about the incenter is equidistant from the three sides of the triangle, meaning that this point right here where all my angle bisectors intersect, the distance from the incenter to the side of the triangles, those were all the same. So how do we apply that to this problem down here? Well, we know that this point G is the incenter, and the length, or excuse me, the length from the incenter G to this point E is 7. So if this one is 7, that means that GF would also be 7, and that means that DG would also be 7 because these three lengths are all equal to each other. So DG will equal 7. All right, so now let's talk about a perpendicular bisector. So a perpendicular bisector, kind of like the angle bisector, is going to do exactly what its name suggests. It's going to be perpendicular to one side of the triangle, okay? So in this case, it'll be perpendicular right here, meaning it creates right angles. And it's also going to bisect the side that it is perpendicular to. All right, so one thing with a perpendicular bisector that's a little bit different from the other ones we talked about is that a perpendicular bisector does not necessarily have to start at one of the vertices in the triangle. So you see right here, this line right here is a perpendicular bisector of this triangle, but it does not actually start at one of the vertices. It doesn't actually pass through one of the vertices. So that's one thing about perpendicular bisector, is that it doesn't necessarily have to. It definitely can. It can pass through one of the vertices, just depending on how the triangle is set up. But the main thing with a perpendicular bisector is that it has to cut one of the sides in half, like it did right here, and it has to create a right angle. Okay, so in this image right here, they've drawn all of my perpendicular bisectors, meaning that they are all coming through. They cut these sides in half, and they're creating right angles all the way around. Okay, so they can intersect inside, on top of, or outside the triangle, kind of like an altitude. It's just dependent on how the triangle is drawn. And then the 3 points where they all intersect right here, that's going to be known as the circumcenter. Okay, and so the thing that's a little bit weird with perpendicular bisectors is that the circumcenter will be equidistant from the 3 vertices of the triangle. Okay, so meaning that if I was to draw lines from the circumcenter to the vertices. Now, this is a little bit different. The lines that I'm drawing in pencil, those are not my perpendicular bisectors. But going along with what this point says, if it is equidistant from the 3 vertices, that means those lengths are equal. But again, keep in mind, those lines that I just drew are not my actual perpendicular bisectors. So next up, we do have a couple theorems that we also use when we're dealing with perpendicular bisectors. Okay, so one of them says in a plane, if a point is on the perpendicular bisector, then it is equidistant from the endpoints of the segment. So kind of similar to angle bisector. So let's look at this problem. AD is the perpendicular bisector of BC. So that means this line right here, AD, it is creating right angles where it intersects with BC and it cuts BC in half. Okay, so if any point is on the perpendicular bisector, then that means it is equidistant from the endpoints. So that means that the distance from D to B is equal to the distance from D to C. So if I want to solve for x, I'm going to do x plus 5 is equal to 3x minus 5. I'm going to add 5 and subtract an x. 10 is equal to 2x, so 5 will equal x. Okay, and then another point that is on this perpendicular bisector is point A. So point A is also going to be equidistant from B to C. So I can set the two equations with y involved equal to each other. So I will add 13, subtract 2y, 28 is 7y, and then lastly divide by 7, and 4 will equal y.